go through the agenda. So tonight we are super excited to have a talk by Sebastian Risi, who is not only a professor at the University of Copenhagen in the area of AI, machine learning, and I believe robotics, but he's also the co-founder and research director of Moodle AI. And we have been following actually Moodle AI's path in the last month and years quite regularly, because we also collaborated with some of Moodle AI's co-founders in the past. So we're very excited to see what Moodle AI is actually doing. I roughly understand that you guys are building a set of AI-powered tools to support game development, but I'm pretty sure, Sebastian, that you can phrase that way more accurately later on in your talk. And yeah, really looking forward to that. I'm really curious to see how you are using reinforcement learning and machine learning algorithms to train agents to perform different things in different environments, which I believe is probably not only interesting for game development, but also for many other areas. And yeah, as in the past as well, we will be using a tool called Slido to collect questions, and we will again give roughly 5 to 10 minutes time for everybody to add their questions after the talk. And then once we have collected questions and voted on them, we'll have a short Q&A session with Sören, probably roughly then at 7:15. And as I already mentioned, we'll be using Slido to collect questions, and you can actually either scan the QR code or go to the website of Slido and enter the event code CAIML 20, and you can already start adding questions already during the event. So if there's something on your mind, you can already add the question. And also to the other participants, you can also then vote on the questions already. So for that reason, I would encourage you to already now open maybe Slido in a different window and start adding your questions there, because then we'll be having a set of questions to vote on in the voting session. Then I think also we probably will share those links in the chat again, so that it's easier for you to quickly jump to the correct Slido page. As usual, we are always super happy to see your feedback, reaction, support on social media. And here in particular, if you're tweeting about our event, we really appreciate if you use the hashtag CAIML or tweet at our account at CologneAIML, because this helps us to spread the word. And of course, once the physical meetups start again, we will also be looking for sponsors again. So for that reason, visibility always helps, and you're doing us a great favor. But that should be enough with the introduction for tonight. And now I would hand over the word to Sebastian, and I wish everybody a great time now listening to Sebastian.
Yeah, today I want to talk a little bit about a different type of reinforcement learning called deep neuroevolution. So, as was said, I'm a professor at the IT University Copenhagen, but also research director at Model AI. So I'm going to talk about some kind of fundamental research we do at the uni, but then I also talk a little bit about what we do at Model AI with these approaches. But happy to answer, more questions if people want to know more about one subject or the other. Funnily enough, my sister lives in Cologne, so I'm actually there also every once in a while. And but I guess right now we're all online anyway, so it doesn't matter too much. Maybe you're familiar with the kind of classical reinforcement learning approaches, and I'm going to go over it briefly, but so you kind of see the difference to what I'm talking about today. But basically, in reinforcement learning, the idea is that you have a state of the world, which could be like when you want to learn to play this kind of Atari games. Then you perform a certain action. The controller performs an action and you get some reward in the game. For example, if you kill an enemy in the game, then you might get a reward, or if you die, you get punishment. And so the reinforcement learning is basically inspired by how animals learn that actions that lead to positive rewards are favored, and actions that lead to negative rewards should occur less. And so if you do this If you train a system like this many times, then it might actually at some point learn to, it could learn to play games, it could learn to control a robot, and so on. And so a big step forward in this kind of reinforcement learning was to actually combine reinforcement learning with neural networks. And in a neural network, basically you have a, like, again, inspired by biology, that we have this kind of neural network where you get something as input, and you have, for example, the controller at the end as an output, like to control which movement should be performed. And what really made reinforcement learning, and I'm just gonna do something real quick, what really made reinforcement learning work a lot better is combining them with the expressive power of a neural network. So in a neural network, I'm not sure how many people are familiar with neural networks, but it's basically kind of inspired very roughly by how the brain processes information, that you have these neurons and they're connected to each other. Of course, it's a very, very simplified model. But if you train a neural network with reinforcement learning, is that you see which actions lead to good rewards, and then you increase for example, the strength of those connections in this network. And some connections you make stronger, some you make weaker. Initially, these networks are all basically randomly initialized, the connections between them. So initially, they will perform very badly. But then if you train them for a long time, ultimately, they will be able to solve the task. And so what this kind of combination of neural networks and reinforcement learning allowed is to actually solve quite complicated tasks and solve them also closer to how we solve them. For example, instead of having to tell the neural network a lot about the game, it can learn to play games based just on raw pixels. It can play two-dimensional, like Atari-like games. It can learn to play three-dimensional games like Doom. It can even learn to play things like StarCraft. Or in this case, for example, work by OpenAI, where they showed it can also learn things like Dota, where you have to coordinate these 5 heroes against another party. But even though there's a lot of progress in this reinforcement learning or deep reinforcement learning, these approaches still work very different to how our brains work, or what our brains can do. So what's typical in reinforcement learning, that you have kind of this training phase. So you train with this robot arm to grasp certain objects that you know. You train it to play a particular game, and then once you found good weights, like these connections in this network that perform the task well, you basically freeze the network. And then the problem becomes that it's not able to basically learn new things. And so that's not a problem if you want the network to always play the same game, to always handle the same type of objects. But if you have to react to things that you didn't know during training, like grasping different shaped objects, then oftentimes these networks will basically fail. So this would be corresponding to that at a certain time in your life, you're learning something, but after that period, you cannot learn anything new anymore. You can only use the knowledge you already gained. But of course, as humans, you learn like throughout your whole life, and you can learn new things. You can adapt to new tasks. And so that's something that in reinforcement learning, that's kind of an unsolved challenge. So these systems, basically, if they encounter something new, they have to be taken offline. They have to be retrained, which can take a lot of time steps. But of course, they can solve complex tasks. And so here are just 2 examples of some of our work that we did. In our case, the network was able to learn, for example, build orders in StarCraft. So this was before DeepMind published their work. We showed that basically, based on examples from humans, we can use those to learn build orders in StarCraft and play pretty well. We also showed that the system can automatically by itself learn to play things like Doom, also just from basically raw pixels. But as I said, there are certain limitations, and here are just some examples of these limitations. Like a neural network that was trained to beat the human champion in this game, this Chinese chess game of Go, on this 19 by 19 playing board, which is a very complex game to play well. But this neural network would completely fail if you deploy it on playing on a smaller board size, which is no problem for a human that can play with a large board. It's no problem to playing the smaller one. Again, here you get human level performance in like this robot that can jump like parkour. But then if something slightly changes that it didn't expect to happen, you get these robots that completely fail and don't perform well anymore. So what could be kind of how can we change these systems to become more adaptive and being able to also learn and react to things that they didn't see while they were trained? So the question is kind of, then in our research group we often look at so what's kind of nature's secret of success? Why can we humans do this? Why can even simple animals learn to walk very quickly? Why can they learn to even if they lose limbs, they can still work well? So how do animals do this so well? And so the secret and the only way that we know that intelligence was ever created is of course through through natural evolution. So this idea of survival of the fittest that maybe some of you remember from school. So the basic idea is simple, right? You have a population and you have some variations. So some of these mice are better adapted to their environment, harder to see for this bird. So these darker mice will have a higher chance of not being killed off, and so they will produce more offspring. So then you're selecting kind of for this particular mice that are harder to see in this case. And so we can also create and this evolution created this amazing, that's one benefit of using of evolution, is it created not just one solution to a problem, but it created this amazing diversity of different ways of like surviving and striving. So it created this leopard, it created, if you look outside the window, it created all this diversity. And of course it also created our brains. And so that's why we try to take inspiration from how does nature solve this? How did nature create biological neural networks, and use those ideas to create artificial neural networks? And just to show you like the very simple idea of artificial evolution. So imagine you're encoding all these different shapes with an array of points in a computer. And then you have some heuristic that tells you which of these shapes is the most round shape. So in this case, it would be, I guess this shape is pretty round. So then what you do is you take this array that describes this type of shape, which is like maybe it's an array of 20 numbers that describe X, Y positions along this. And then you just add a little bit of noise to these numbers, like just slightly changing them, and you create another 6 of these circles. And in this case, you're not only choosing one, but you can also choose multiple ones. And then you might take some parameters from this model, and you take some other parameters from this model, and then you add some noise, and then that's the outcome. And then you repeat the process again. You choose the ones that are mostly look like a circle. You again choose them, and you add a little bit of noise again. And then at some, like after some generations, in this case it's just 3, it might take 100, it might take 1,000, you reach like a solution that you're pretty happy with. So one benefit is of this artificial evolution that it's very domain agnostic. So you can, anytime you have some parameters, you can apply this idea of having a population, having like some mutation, which is just like noise, and this idea of selecting like some criteria. In this case, the criteria would be which shape is the roundest. And this has led to kind of one benefit is that it is actually quite that it can come up with solutions that we humans might not have thought about, and that's why we also use it, for example, for game testing at Model AI. So one example here is that artificial evolution was able to create these antennas, and one of them actually went to like a mission to NASA, which this is made by a colleague, Hornby. And these antennas don't look like human design antennas, but they're really good antennas. And it's just that evolution was able to design, artificial evolution was able to design these antennas, which might not correspond to how we think an antenna should look like, but they were evaluated to have very good properties, and evolution was able to basically design them. In this case, evolution was able to, for example, add a part of the antenna, remove a part of the antenna, reshape it, and so on. So these are the kind of mutation operators for this antenna design. Also, the same horn, we also use this to design like kind of look like IKEA tables, where also the goal is just to have a stable table, and the algorithm is able to come up with all kinds of different designs by itself. So that's an example of how this kind of artificial evolution can be creative and create things that a human might not have expected. And so we're of course also interested in, can we use those to control agents in games, which can be used for game testing? Can we use those ideas to come up with neural networks like that control robots? And so instead of evolving like table designs or antennas, we have a population of these robots or agents in a game, and then what we do is that we evolve we change their artificial neural network. So we have this large neural network, and we have initially like maybe 100 networks, and we try them in a game. Some of them will perform better than others, and then we add noise to those parameters of those networks, and then we test them again. Some of them will perform better, so we take those, we add noise, we combine the best parents with each other, and over time they're able to figure out how to solve a particular problem. And so it's amazing, like in the last couple of years, that this actually works. Like you can take a neural network with 4 million parameters, and the only kind of you can implement this whole thing in 10 lines of code. You take those parameters and you just add Gaussian noise. You have a function that evaluates how good this network is, and then you just make more offspring from the ones that perform well, and you remove the offspring, the neural networks that don't perform well. So it's a quite simple method, and it performs in some cases competitive to also more complex deep reinforcement methods. And so then what we wanted to see is if we apply this method and also reinforcement learning methods on tasks that hasn't seen, where are the kind of advantages. And so in this case, we have this kind of ant-like robot, and then we wanted to see what if we train it on the functional morphology, and we train it also on one where we cut off a leg. And what we then tested on, so those are the two things it sees kind of while it's trained. But then when we test it, we actually cut off another leg, and then want to see how good is this agent, this robot, in adapting to things that it has not experienced while it was trained. And so if we see here, this agent is okay at walking with the two variations that it has seen, but then if we test it on cutting off another leg, it doesn't perform well. It doesn't perform well at all. While like a biological organism would likely, like a dog or cat, like I, for example, had a cat when I was a kid that had 3 legs, and that was totally fine walking. Of course, it needs some time to adapt to that, but these artificial agents cannot do this very well. So what's the reason why that doesn't work? And so that's some work we published last year where we extended this idea. Like basically, what I told you so far is just the first part of the story, is that our brains, what the actions you do are determined by the strength of the synapses in your brain, like how strong is the synapse, and you have billions of those, and that determines what you will do. But of course, the other thing in our brains is that the mechanism that adapt our brain, that help us learn, are also learned through evolution. So you can learn new things during your lifetime because there are mechanisms in your brain that know, okay, if these two synapses always fire together, then maybe the connection between them should become stronger. If those two synapses always never fire together, maybe the connection between them should be weaker. And so that's one of the simplest mechanism that our brains learn. And this mechanism is called Hebbian learning, Hebbian plasticity. So if two neurons always fire together in your brain, then the connection between those two will likely become stronger. This is basically a description of this process, that you have this weight in your neural network, and the change of the weight should be determined based on some learning rate. And then the activation of what is called the presynaptic neuron and the postsynaptic neuron, and different combinations of those. So what was our idea then is to instead of learning the weights of a neural network at all, we only learn how these networks, how every connection in the network should change based on how the activation it gets as input. So in this work, the agent actually starts, and if you look briefly, it's so every time the agent is born, so what you can see here is a visualization of the weights of this neural network. So every time the agent is born, it starts with a completely random connections. And the only thing we learn is these Hebbian rules, these learning rules, and we find those learning rules with evolution, how to change the weights in the network. And if you can, and then you can watch here how the network basically changes throughout its whole lifetime. So in contrast to normal reinforcement learning, where we would learn and then freeze the weights, here the weights are always changing while the agent interacts with its environment. And so we show basically that in this approach, the agent is able to walk with all three types of morphologies, also when one of the other legs is cut off. Whereas if you just have a static network, like the typical reinforcement learned network, it basically fails when we cut off the leg it hasn't seen. And then we also applied, of course, we're also interested in games. So for game testing and things like this. So we also applied this to, like, for example, here in this very simple demonstration in this car racing game, where again you see that the network is not static, it's changing throughout its whole lifetime. And it's again starting from completely random weights. In a few time steps, this system is able to stabilize, or not stabilize, but find weight patterns that work in controlling this car. So then the next kind of thing is to, now that we have the system, this artificial kind of evolution, can we also use this to add humans in the loop, for example, which is important if you want to generate new game levels or something else. You don't just want the computer doing the work, but you also, of course, want to have humans in the loop to guide this kind of process. And so that's also one thing where these artificial evolution approaches are very good, because we basically already have been doing for a long time, have been involved in evolution. Like, we choose which cats and dogs we like, and they have a better chance of, like, dog breeding has a long history that we now have very different dogs than, like thousands of years ago. So we have been doing kind of animal breeding for a long time, because we can guide this kind of process of where evolution should be going. So we can replace this natural selection with some kind of human selection, and so we can do the same thing in a computer. And so one example I wanted to show where you can basically, we allowed casual users that have no idea about neural networks or artificial evolution, we allowed them to create controllers for Super Mario just through the process of selecting what type of Super Mario they like. Okay. So basically, in this case, we present the user every time with these 9 screens, and then the user just chooses which of these Super Mario behaviors they like most. And initially, they're all controlled by neural networks. And initially, these neural networks are randomly initialized, so they're not doing anything useful. They might just run into the corner. But then you can choose the ones you like, and basically when you click on it, then it creates, basically it takes that neural network that controlled that Mario, then you create 9 copies of it, add noise to those copies, and this is the next generation of Super Marios that you see. And by doing this process of artificial breeding a few times, at the end you can actually get to Super Mario behaviors that perform quite well and play the game quite well, even though the users that use this system had no idea about machine learning, about neural networks, or anything else. So it allows, basically, it enables casual users to come up with controllers and not just like content for games. And here are some examples of after 15 generations, which means like 15 clicks that the user had to do, what kind of Mario behaviors we get. And it's nice that you get you get also diversity. They're not all the same. So this is I'm going to kill everything that moves Mario, which is quite aggressive and is shooting at everything. Then we have another controller that was apparently made by a lawyer with no knowledge of AI, but by doing this kind of artificial breeding, that person was able to make a controller that is not as aggressive, but just runs to the level very, very quickly. So basically, you can have humans guiding the search, and having the humans in the loop allows you to create kind of more diversity in the type of controllers that you get. So kind of one of the last things I wanted to talk about. So now I showed you some experiments from this artificial evolution that we do in the uni, but we also do it in the company. But also, of course, deep learning has also a lot of advantages, or deep reinforcement learning. So can we kind of combine the advantages of both? So artificial evolution allows us to create a lot of diversity. Deep learning is good if we have if we want to learn from a lot of data. We have, for example, a lot of examples already. Then can we kind of combine the best of both worlds? So maybe you're familiar with these generative adversarial networks. If I was there in person now, unfortunately, I can't see people are raising their hand, but I would have asked you if you know any of these, if you have ever seen any of these people, like are they famous actors? And then I would have told you that you probably never saw them before because they're all not real. So all these faces are generated by a neural network, and this was 2017. So now we have much better methods that look even more realistic. But basically how this system works, and I'm going to explain it very briefly, but this is what's called a generative and adversarial network, which has been very popular in creating all kinds of content like faces or other content. But basically how they work is that you train them. You basically have these two networks. One can generate a picture. The other one is a discriminator, has to say, is this image real or fake? So every once in a while, this discriminator, this neural network, gets either a real image of a person or an image of a person that was generated by this other neural network. And so over time, this generator gets better. So basically, the generator is a forger, and this discriminator is a detective. And so the forger gets better at making things that cannot be told from real or fake by this discriminator. And then at some point you get a system that is able to generate all these different faces or other images that don't really exist in the real world. And so we wanted to see then also, can we use this for generation of levels? And of course, everybody's favorite game as an AI researcher is the Super Mario game. And so what we did here, and I'm borrowing this nice video that the Science Journal made about our work. What we basically did here is the neural network, this generative adversarial network, analyzes a lot of existing Mario levels because we have a lot of already existing Mario levels. And then once they're analyzed, we actually using artificial evolution to search in the space of all kinds of levels that can be generated by this generative adversarial network. And here are those two phases, basically. We're learning, we're training a generative adversarial network, or also short for GAN, an existing content. And then in the second phase, we're basically, and if you're familiar with GANs, what we're doing, we're evolving the latent vector that goes into the GAN, and we are optimizing that vector to create levels with certain properties. For example, can we create a level that requires very many jumps, like an example like this, or can we create a level that requires almost no jumps from Super Mario? And the same, for example, in this overworld and underworld level. So we can guide a trained generative adversarial network, combining it with evolution, searching in the space of things that this network learned, and we can use that for example, for level design, finding levels with the right difficulty for the user. You can also imagine finding levels with the right aesthetics. And this is one thing that came out of this collaboration of our company Model AI and King, that you might know from Candy Crush. So we use the same system to generate Candy Crush levels with a certain that have a certain difficulty. And so again, here you have like thousands of levels you can train from, and then you use the system to come up with levels that make sense, but that are still new and have not been played by a user. So this was one research collaboration that we published in this COG conference also last year. And then this is another like example of how you can use those methods in, oh, it's not automatically repeating, it's a very short video. But basically what we also use this for is like for game testing. So because these evolutionary algorithms are good, because they create a lot of diversity, so if you want to make sure, like one main area of our company Model AI is to create approaches that can play a level, play games, and find bugs in levels. Like for example, can you clip through the wall, or are there any graphic bugs? Can I always reach the exit from the starting position? So we're using ideas from these evolutionary algorithms that can create a lot of diversity with ideas from reinforcement learning that can learn from human examples to be able to accelerate, for example, game testing to try to find all kinds of different bugs in a game before it has to be shipped to the user. And so that's kind of concluding my talk. Like evolution is good at generating a diverse array of solutions, which is good for creative applications such as games. It's good for applications such as like bug searching, and because it is like a very diverse search method. And then we have also seen that this kind of hybrid approach is combining, for example, generative adversarial networks with evolution kind of allows us to benefit from the advantages of both methods. And in the future, I think we can really push those methods to allow us to help in like with designers coming up with new levels on the fly. It can help us with agents that can play games similarly to how humans play games, telling us, are these levels balanced? Are they broken in some way? So I think they can really help us to also revolutionize, I think, this like game development as well. And with that, I want to thank you very much for your attention.
Great, Sebastian. Thank you very much. It was really a fascinating talk, and also I really love that you had so many images, videos, and examples. I now really feel like playing Super Mario. But actually, maybe I need to wait a little bit and maybe just quickly share my screen again so that I can everybody show the link to our, all right, you should see my screen again. Yeah, maybe before sharing the link to Slido again, one favor that everybody could do, and this is giving us feedback. Sharing here a link to a very short SurveyMonkey questionnaire, which asks you 4 slides, and this really helps us to understand what kind of topics, talks, and content you guys like. So we would really appreciate if you take 2 minutes and fill out the survey. But now, again, the link to Slido. And I have already seen that people have started to add their questions already. I think we already have quite a few. Nevertheless, I would give everybody 2 to 3 minutes time to vote on the questions and maybe add questions if there are more questions to ask. And yeah, then we can go through the questions and see how far we get with the questions. And then, yeah, maybe let's give everybody 2 to 3 minutes time, and then we'll start with the Q&A. And I will also be sharing my screen and show the current questions. All right, as we have already plenty of questions, I don't think that we actually need to wait longer. Maybe Sebastian, do you want to just read out the questions and answer them? Because we have seen in the past that people tend to not rather speak up and read their own questions, and it's often easier if the speaker just goes through the questions and I will just check them off as you answer them.
Sure, yeah. I can start from the top. So do you see or foresee use case on industrial applications using deep neuroevolution? Yeah, I think, I mean, industrial applications, I think everything where you kind of need to create more diversity, like for example, one industrial application is of course also design. So a lot of like design companies like Autodesk, like generative design, where you don't want to have just one solution maybe to your design problem. There you can use artificial evolution to get some ideas of a diversity of designs that are, for example, like car designs, but they still have some minimum criteria that they have to satisfy. So for example, being stable. So you can have like humans in the loop in these applications. I mean, we use it for level design, but also use it for generative design in architecture, for example, as well. What is a game you would love to generate levels for, but might be too challenging currently? Yeah, that's also a good question. So one thing that we're we're currently more on the university side, less maybe we're focusing less on it model AI, but we're using generating artifacts and levels in Minecraft. So one thing I think was very cool about Minecraft, that you can have static structures, but you can also have dynamic structures like moving, like machines that move and that do something. So we're currently designing systems that can learn to create increasingly complex machines and levels in Minecraft. So that's definitely one system really interesting. Could also be cool to do maybe automatically generate, and there's some people that did some, like also Julian, who's one of the co-founder of our company, and also research director, not only creating the levels, but can you create completely new games? So can you create like the rules of a game? Can you create what happens if those two objects collide? Would be super cool to do something like this. And can you automatically create new Roblox games or something? So it's something we haven't, like nobody has tried that, but that could be something in the future. Could be really interesting. Does the product of Model AI build on top of a particular platform, Unity? Yeah, so we have support for Unity. So that's one of the big things that we're supporting, the Unity platform. But then also we have an integration for Unreal as well. And we're also working on other ones. So if any people here that are interested in using those systems, definitely reach out. We're definitely working on supporting more and more different platforms. Having several neural networks as agents simultaneously sounds very expensive. What is the performance of these models? Yeah, so it's like artificial evolution does require you to simulate a large population of agents, but you can also parallelize that really well. So in that sense, it's actually similarly to reinforcement learning, where you also need a lot of rollouts. You need to simulate a lot to get kind of some signal to train your agents. So it's not that much more expensive. It's just that you spend your resources on a slightly different in a slightly different area. But because it's so easily to parallelize, you can just basically run all those evaluations in parallel. It really is easy to parallelize and running it across a lot of like multiple CPUs, for example. Also, if there are follow-up questions or somebody wants to say something, or it's not so clear what I said, just stop me. Otherwise, I just keep going down this list. Have you seen applications of these models in natural language processing, for example, chatbots? Going into the direction of general AI with this question. So yeah, that's one area where I have not seen so much evolution, like artificial evolution would be interesting. one thing I could imagine that would be interesting, you can kind of, if you have a language model, you can try to probe the language model with artificial input to see if it would generate anything that you don't like. Like, what kind of prompt do you have to give it so it generates something racist? So you could use those approaches to check, is your model, that your model is not producing output that is, output you don't want. So instead of using it to train these models, you could use it to check that these models did not learn something that they shouldn't have learned. Isn't artificial evolution identical to genetic algorithms known for quite some time, or what is the difference now? Yeah, they're exactly like genetic algorithms. So it's just a different name. The difference is now that we basically have more compute. That these simple algorithms that we people invented, 30 something years ago, that these algorithms now scale a lot better because we have better training methods. And that's basically one of the only differences. So sometimes it's just about the scale, but these one of the approaches I showed you, these static neural networks, we would have had the same technology, maybe 20 years ago. It's just that we didn't have the necessary compute maybe to do those. So from an approach perspective, some of these are relying on quite simple methods, but work quite well. How do you investigate and map the latent space of the Gans? Architectures like bicycle GAN? No, so we just use a normal GAN, and then when you have a normal GAN, you put in this latent vector into this GAN. So basically, it's just normally what you put in the GAN is just random noise, and then you put in random noise, you get an image out from what it learns. So you put in a random vector, and you get a different picture out. And what we do is, instead of putting in just random vectors into the GAN after training, we try to find a vector that generates a level with a certain difficulty. So we put in 100 vectors, and we see which one of them produces a level with certain properties. Then we take that vector and slightly mutate it again. We add some noise to this vector. Then we create copies of it, put it in again, and see. And over time, we find a vector that has particular properties that we like, or the content that it generated has particular properties that we like. In the GAN networks, how does the critic work for level generation, for example? Like, what kind of comparison it does? So basically, this critic, what exactly it does is it's not 100% clear, because it's basically, the critic is also a neural network. It takes as input an image, and it outputs, is this real or fake? So basically, the learning algorithm determines what does the critic learn. So the critic, at the end of this training, for example, might look at certain parts of the image. It might look at certain parts of the face to know if it's real or fake. But that's basically learned. So the same way we don't know, or it's difficult to analyze exactly what the network does when it recognizes images. It's the same way that after the work is done, it's not exactly clear what the critic does. You have to actually look at it, you have to dissect it, you have to probe it to kind of get an understanding of how does it look at those images. But it's basically, it's because it's trained, it's a little bit like a black box that you, at the end of this process, it's not 100% clear what it does internally. Then is this the only way for continuous learning? How is it done in RL, or isn't there a way yet? Yeah, so there are, of course, some other approaches people work at. So some people work on like you learn one task with a neural network, you learn another task with a neural network, and then you kind of merge these two networks together without forgetting what you previously learned. So there's this kind of idea called progressive neural networks. There are some approaches that try not to change weights too much if they are known to be important for a task that it has learned. But none of these approaches are, and also our approach is also, of course, not perfect. So none of these approaches allow this continual learning or adaptation as good yet as what we humans do. So there's a lot of room for research in that area. Is socket-based communication interfacing between the agent and the environment a valid approach? So oftentimes you have already an API. So oftentimes in these examples we use at the university like this OpenAI GIM interface. That's what it's called. So instead of having a socket, you get like a list of observations back from your environment, like for example just pixels or maybe the distance to objects, and then you decide you send back the action you want to perform. So it's you could probably implement it also a different way, but that's how it often works. You just get a list of observations back, and what you send to this API is the action you want to perform. Take a little sip. What kind of evolutionary algorithms can be used for that? Also things like ANT algorithm. Yeah, so we often use like some approaches a very simple genetic algorithm. We also use what's popular right now is also what we also use for this learning these Hebbian rules. We use a evolution strategy. It's another type of kind of evolutionary algorithm, but I have not used like ant colony optimization recently for these approaches. It might also work well, but we focused on other algorithms. Then could those Hebbian learning rules in principle be applied to static solutions like classifiers in DL to replace optimizers like stochastic gradient descent? Yes, so there's actually approaches. There's one paper called, I think, learning backpropagation and improving it. So you could learn first with this similar system how to do backpropagation, and then you could learn to do better backpropagation that is tailored to the particular domain that you're trying to solve. So that's definitely a paper I can suggest if you're interested in it. I think it's called Learning Backpropagation and Improving It, it's the lab from Schmidhuber's lab that do something similar to that. How do you adjust games that have predefined levels? For example, in a quiz, can we use Neuroevolution to adjust order of questions to adjust the difficulty? Yeah, so the nice thing is about evolution or artificial evolution is that anything that you can it's basically so domain agnostic, you can apply to almost anything. So if you can find some representation, like if you wanted to adjust the order of questions, what you could do is you have a certain order of questions, and you give it to like one challenge is if you want to give it to a population of people, then it's quite costly. So you can make these questions, you can have different orders, you can give it to different participants, and then at the end you see what is the kind of criteria that you want to optimize. So maybe you want to optimize for a sequence of questions that is the most challenging or the least challenging. So as long as you can generate this kind of diversity, and as long as you can have a mutation operator, in this case it's just ordering different orders of questions, then you can basically use artificial evolution algorithms. What would happen if you let two neuroevolution networks compete with each other, for example, in chess? Would they adapt to the opponent or find the optimal play? Yeah, so this is one area that is very popular right now. It's popular in neuroevolution. It's popular also in reinforcement learning. And it's this idea, basically, it's called self-play. So you have one agent playing against another agent, and they're getting better and better by playing against each other. And so this approach has been used also by DeepMind for making their StarCraft agents perform really well. It also, a similar approach has been used to train agents to play Go really well. So this idea of incremental, it's basically of co-evolution. You have one agent that plays against another agent getting better and better. So you find this idea under the name of co-evolution or self-play is very powerful and has really also resulted in really good performance. How are Gans for games different from classic Gans? So, I mean, we use basically a very kind of classic Gan for this work on Mario and Candy Crush. One thing that's different in these games is that they have oftentimes a discrete representation. So like while you have in image of faces, you have like, you know, like floating point values, color images. When you have game levels, you have more discrete representation, that this tile could be like could be a pipe, or could be a Goomba, or it could be Mario. So that's one difference. The other difference is that it's much harder actually to generate game levels than to generate faces, because in game levels, it's also a requirement to be functional. So you can create a very nice level, but if the level does not allow you to go to the end, it's not playable. If the level generates only a door, but not a key, you cannot solve this level. So while it's not so important if you generate faces, okay, there's 1 pixel wrong, or there's 2 pixels wrong, but if you generate a game and you're missing like the keys to open doors, then those games would not be solvable, and so then there would be no point in generating them. So generating game levels is quite challenging, because they need to look good, but they also need to be functional.
Great. Thank you very much, Sebastian. Also, thank you very much for answering all the questions. I think there was maybe yet another record in answered questions per minute. But I'm very happy to see that there was so much interaction and engagement today from the audience. And I think there were quite some really interesting questions today. And I can read from the questions that also some people might be really eager to test those kind of things. So thank you very much, Sebastian. Really appreciate that you took the time, gave this really nice talk. And also answer the questions. And yeah, if you ever happen to be in Cologne, feel free to reach out if you want to catch a lecker Kölsch or something like that. So
it would be nice to meet in person, have a beer afterwards. But yeah, I'll maybe it works next time. But yeah, thanks again for the invitation. And so please, yeah, definitely reach out if you're interested in our uni work, in the model AI work. Just shoot me an email. I guess probably somewhere on the meetup page. And I can also provide the slides if people are interested in having a look at those.
I mean, yeah, that would be really great. Probably we'll be sending a message to the group later this week once we have the video ready, and it would be great if you can send us the slides, because I think it would be really great for further reading. And maybe next year when there's Gamescom, I'm not sure if you guys will be attending Gamescom. That would also be an opportunity maybe to have another in-person meetup or something like that. We did that a couple of years ago. It was very well perceived, and maybe next year we can get back to that. But yeah, maybe then we can just talk again.
Okay.
Great. Yeah. Before saying goodbye to everybody, just a final reminder for our survey, and also a heads up regarding our next meetup. So the next meetup will also be a virtual meetup for sure, because we will have again a speaker who is not within the area actually, and we will have Barry Kersbergen. He is working for Bowl.com, and he will be talking about retail recommendations on billions of interactions at Bowl.com. Also a very exciting talk, and it is actually also based on a paper that was recently published on the International Conference of Data Engineering. And yeah, we already look forward to that talk. And yeah, then I would say thank you very much, everybody, for attending. Thanks again for the great talk, and have a great evening, everybody, and hope to see you soon, and hopefully also in person then.
Thanks. Bye.
Goodbye.
Thank you. Bye.
Goodbye. Have a good evening.